Okay. Then welcome to this seminar again. And today our speaker is Lukasz Wozny from Warsaw School of Economics. And Lukasz is the associate professor at the Department of Quantitative Economics in the Warsaw School of Economics. And his main research interests focus on stochastic games and large games, economies, and consistency, control, self-control, so behavioral topic, general equilibrium models, recursive competitive equilibrium, among others. And he has very nice papers, some papers in Journal of Economic Theory, International Journal of Game Theory, Economic Theory, and Journal of Mathematical Economics, Games and Economic Behavior. So he's a very successful researcher and a very nice colleague. I know him personally. So today he will speak about time-consistent equilibrium dynamic models with recursive payoffs and behavioral discounting. So thank you for accepting our invitation, Lukasz, and the screen is yours.
Thank you, Miklas, for introduction. Yes, so thank you for thanks. I would like to thank the organizers for giving me the chance to present this work, and obviously for all of you for participating. As have been said, this is a work in which we seek for time-consistent solutions in a very general class of dynamic models with what we call behavioral discounting, so that the discounting would be quite general to allow for many behavioral features. And perhaps the interesting or notable characteristic of our work is that we can also apply the techniques to recursive payoffs, so not necessarily separable between preferences that are not necessarily separable between the periods. So this is the joint work with Lukasz Balbus that we were chatting about from Zielona Góra and Kevin Reffett from Arizona State. All right, so I guess I don't have to spend too much time in convincing you that discounting is critical in dynamic models. If you think about growth or consumption savings, that's obvious. But obviously, if you think about normative considerations, when you think about, for example, justice between generations, or you think about cost-benefit analysis when doing some environmental economic assessing some environmental policies, or general, welfare policies in some macro models, the role of discounting is crucial actually. And broadly speaking, there are a few ways to attack the problem and to understand the role of dynamic preferences and discounting in particular. So one focuses on axiomatic foundations, and here obviously the seminal paper is Koopman's, but many others that followed, and more recently focus on trying to axiomatize various behavioral features actually. And obviously the same is confirmed by the lead from a different perspective, obviously, in experimental or empirical work that document various departures from exponential discounting on the side of, as I said, experimental and empirical data. Perhaps surprisingly, the same considerations are present also at the normative level. So if you think about, I mentioned already, justice considerations or environmental foundations, but also if you think about sustainability concepts, this this makes you question the applications of exponential discounting to such problems. And the last bullet here, most recently perhaps, there is an interest in what is called the collective decision-making problems, where you have, for example, the collective household of collective agent economy, and you're trying to design the sequence of consumptions for individuals so that you maximize the sum of their utilities. And even if all of them are exponential discounters, it happens that this collective preferences happen to be non-exponential generally. So there are various motivations lead us to this thing that that time inconsistency problems that are associated with most of those, perhaps apart from exponential discounting, it's inevitable in a sense. So here by time consistency problem, I mean that whenever you choose the sequence of at the point S in time, whenever you choose the sequence of decisions, so the consumption decision, for example, for the next period, let's say from small to large t, and the large t could be infinite if you like, and that decision will change with the decision date, right? So it will change with S. And there were various attempts to understand or to show existence or analyze time consistent plans in such settings. And obviously the first reference is Strauss, who defined or who mentioned that we should actually focus on the best or the optimal among those plans that will be actually followed. And well, I mean, the problem with that approach is that it is shown that in some examples, important examples actually, such solution may be non-existent. Actually, and this is, you know, partially due to the fact that that in models with changing preferences, you can lose continuity on the set of time consistent policies. So some solution has been offered by game theory, where people switched from the, you know, decision tree approach and used the notion of subgame perfection or Markov perfection, and using that approach from that language from the game theoretical solutions, try to prove existence and analyze the appropriate subgame perfect solutions in such models. And that was done by Phelps and Pollock, or Pelek and Yari, and many other that followed, obviously. And at this point, I should mention that these two approaches are not one-to-one, in a sense that they differ. They differ, for example, in the way they treat indifferences. So, for example, if you think about decision theoretical approach, and that quotation from Strauss I mentioned a minute ago. So if you think, for example, that the current decision maker is indifferent between some alternatives, it may be that the earlier self have a strict preference relation over this. And well, if this is true, then you should perhaps think that you should resolve such indifference with respect to preferences of the earlier self. Precisely for the reason, as Strauss mentioned, that you should focus on the optimal plans that will be actually followed. Well, these considerations are not present if you think about dynamic games, because well, because Nash equilibrium is a weak concept. So any of such any way you break or resolve such indifferences is available, is eligible actually. Well, obviously, you can claim that that such indifferences are negligible, in a sense that their set is small, and this is precisely the idea that is somehow underlying the stochastic games approach that was, you know, initiated by the work of Harris and Leibson, for example, who managed to write the Euler equation for the Markov perfect equilibrium in the quasi-hyperbolic discounting model, and it's obviously generalized because the preferences start changing over time. So we lack the principle of optimality. And me and my co-authors also applied the similar kind of techniques, but we rather concentrated on the primal. So we didn't use the first order characterization, but rather adapted the Bellman equation in a sense, in such a way to account for changing preferences. And some flavor of that is also present in the current presentations. I will go back to that. And the last bullet here talks about what is sometimes called the dynamic programming squared. And this is basically the idea to use the self-generation techniques developed for repeated games in such problems of models with changing preferences, and this way characterize perhaps the set of sequential solutions or sequential equilibria to such problems, and that was started by Kedlan Prescott, Bernheim, Ray, and Yeltekin. And we also have a parallel paper where we develop, it's somehow related to the one I'm talking today, that is studying this problem in the context of altruistic growth economies. All right, so the last comment before I jump into the details is that many of the things I mentioned on the previous slide were somehow specific. That means that they managed to work, that it is designed to work for example, for quasi-hyperbolic discounting, because this is so useful and so easy in a sense to apply. It has two parameters, beta and delta. It is well known. And well, obviously, the most simplifying assumption underlying the quasi-hyperbolic discounting model is that, well, you somehow believe that from the next period on, you will be exponential and consistently use the discount factor delta. And yeah, but as I said, I mean that there is a growing number of papers documenting that that from the empirical, experimental, or normative considerations, we should think about more general forms of discounting that we will call behavioral here. And also that we should also think about non-additive aggregators to account for various problems that you want to analyze. And there are some great surveys of these problems, but obviously I will not have time to talk about all of these applications. So yeah, so to set up the language or notation, think that we have what we call behavioral discounting preferences, and we have the dynastic representation presented here, so that at every period t in time, every generation is using the sequence of delta taus actually to assess the future utility streams. So as you see, I mean, generally these preferences are non-stationary because this delta t could vary with time, you know, in a free way. And yeah, but it's time invariant in the sense that every period we have the same preferences. And using that, you can assess the discount rate between the consecutive time periods. And we say that this preferences, intertemporal preferences, are somehow misaligned whenever this ratio of delta t plus 1 over delta t varies with t. So it's not constant. For example, it's not constantly equal to delta, but it varies with time. So this is very general. In a paper, we are even more general than that, and I think I will, time allows, I will also mention these other generalizations here. But I think that this is somehow the starting point. And obviously, the exponential discounting is a special case here. Quasi-hyperbolic is a special case here. The hyperbolic model and various other models of discounting are special cases of the formulation of one. All right. So well, what's our aim in this paper, and what we show actually in the paper is that we show two things. We show existence of what I call the recursive utility. Well, obviously the preferences are time inconsistent. So you will mean what I will show you what I mean by that. And we also show existence of stationary Markov perfect equilibrium in such the games representing this problem. And thus we are somehow linking the recursive approach with that of dynamic or stochastic games. And as I mentioned, we managed to do it allowing for non-additive structures, so more general than the one you've seen in the previous slide. And also we managed to do it for unbounded utility functions. But I will not concentrate, if you allow today, on this because the notation will become cumbersome. So for today, let's think that this that either the state space is compact or preferences are bounded or the rewards are bounded. All right, so here's the notation. The horizon is infinite. Well, the important thing is that we concentrate on consumption savings problems. So you will see what I mean by that in a moment. And we have a sequence of generation. Each generation is given some state. That could be the capital or production level or asset level, ST, and the generation would divide it into consumption and investment, so that to obtain utility from consumption, and investment would parameterize the possibly the random transition to the next period state ST plus 1. This restriction that we have, that CT belongs to 0 ST, it's without loss of generality in a sense. Well, the state could be interpreted here very generally. So we can, for example, involve some borrowing constraints, some lower bound of borrowing, etc. So, but you can see that the language is quite general here. And what else? Yeah, and we have utility. Obviously, there's continuous, strictly monotone, and I would add later on some other specific assumptions, obviously, concerning that. So this is the notation, and yeah. So I will start to fix the language. Let me start by quasi-hyperbolic discounting and show what is the essence of our approach. So here you see that, yeah, we have W, which is the value of the consumption stream evaluated from the current perspective, where we have this extra impatient parameter, typically beta delta. And so from the next period on, we have a different value, which we call U star here. And that value is basically assessing what you think, how you assess the preferences from the next period on. And that's discounted using delta. So actually, U star will be yeah, well, yeah. Let me just show that. Obviously, whenever beta is not equal to 1, then the W and U star are possibly different, right? So that's the problem with the lack of principle of optimality here. All right, so here we have a definition of the Markov perfect equilibrium. That is sample best response and any period T and any period and a state S to the sequence of C star T plus 1 from the next period on applied and evaluated using our preferences, beta delta and U star. So that's a definition, and we're gonna, I mentioned already that we managed to prove even the existence of even stronger solution concept, which is stationary. So that would mean that the C star is the same for every T. It's constant with T actually. But that will come. So I think this is quite standard. All right, and the starting point to somehow see the essence of what we do is the following. And I'm citing one of our papers, but obviously we're not the first one to realize that there is a way to link U star with the W, so that the next period value and the current period value. And how you can do it? Well, basically what you do is that you are maximizing the current period preferences. So U of C plus beta delta expected U star. And then to get back to U star, what you need to do is basically, well, you have to divide it by beta, so that to get rid of beta here. And then you need to correct to have U of C star again, right? So you have to subtract 1 minus beta U of C star and add U of C star, and then you'll be back to U star. So this is what we call the generalized Bellman equation, because it somehow links the Bellman equation part where you optimize for a given value, and then you have the corrective factor that accounts for changing preferences. And since this is beta delta model, this corrective factor is so easy to explicitly, write here. All right, so we have this, and And well, what we realize very quickly is that this additive structure here, it's not helping us a lot actually, because whatever we do could be applied to even more general form, where you actually can express the problem using the aggregator V that has three arguments. The first argument is basically current consumption or utility from current consumption. That would correspond to this part. Then you have, well, the last one is the continuation utility that it's obviously somewhere here. And you have a middle one, which is the new one, which would be the corrective factor I just mentioned. So that in this formulation V, you see that, well, we are linking some sort of a recursive part with the strategic part, in a sense that you're gonna maximize or you're gonna best respond here, not only to the U star, which is the utility or the value, and a C star itself. So that's what I mean, that we are linking the approaches of recursive utility and dynamic games, for example. So here you can see that whenever you find the C star T that belongs to the argmax of the right-hand side, we will have the Markov perfect equilibrium as defined previously. So yes, so now I will specify some assumptions on V, and show you, under what assumptions on V we can claim existence of this solution concept that we are interested in. All right. So as I mentioned, I'm skipping some of the local boundness assumptions here because of lack of time and space on slides, but as I will concentrate on the merit things. So the first thing says that this aggregator V, it's monotone, meaning that it's increasing with the current utility and the current consumption and the continuation utility, and it's actually decreasing with this corrective factor, and that would account for the case where, for example, beta is less or equal than 1. So that is assumption particularly useful for this one, but I will show you how we can generalize that monotonicity with respect to middle argument later on. Well, we want to have some contraction. Oh, sorry. We want to have a contraction of the last argument, and it's obviously satisfied for this quasi-hyperbolic discounting model. So that would be the other thing. Now, the key condition that allows us to solve for the Markov perfect equilibrium would be that whenever you calculate the difference of V with respect to investment, all right. So here, that difference satisfies the single crossing property with respect to S. So we have basically single crossing with respect to investment and S, and very importantly, it's strict single crossing. It means that if you calculate the difference between the two investments, that function is a strictly single crossing function with respect to S. So it crosses 0 only once from below. And that would imply that we will have every selection of investment that will be increasing function. And that must happen actually for any continuation and having a corrective factor. So it's a little bit more general than I just mentioned, because we have to take care that investment obviously parameterizing the future. But in many, as for example, many cases I will show in a moment, this is very easily to verify. And that's what I mentioned in the beginning. As I said, that we focus on consumption saving problems because this condition number 3, it's precisely presented for consumption saving. But the idea that we apply is obviously more general, so you can adapt it to a more general class of models. But that condition is precisely expressed if you think about consumption saving issues. All right. Oh yeah, I always some assumption about Q, of course. So we assume that Q is monotone and continuous in the stochastic meaning. And the last one is perhaps interesting, that the number of the set of investments that takes you with a non-zero probability to a particular state is at most countable. So this is, for example, obviously satisfied for the deterministic transition, where you have one-to-one map between the investment and the next period state. And another interesting application of this, the example of this satisfying this assumption is, for example, where Q is non-atomic, where then the set of investment that takes you to a particular state with strictly positive probability is empty, and that is also satisfying condition number 5. So, but there are many other conditions that, many other examples that you can produce, but perhaps these two are the most interesting ones, I would say. And then, then we have our results that there exist stationary and Markov perfect equilibrium and pure strategies. That is, there exists a function C star and U star that solves this generalized Bellman equation. All right, so that if you think that tomorrow's continuation would be U star and you adapt the corrective factor C star, you would best reply by C star and you will go back to U star again. So that's these are the assumptions we adopt. As I said, I missed the assumptions concerning boundness or local boundness, but that's because of space and time. But you can find it in a paper, obviously. All right. Some examples. In particular, we obtain existence of a stationary Markov equilibrium in the deterministic quasi-hyperbolic discounting model whenever utility is strictly concave. So the strict concavity of the utility is precisely the condition allowing us to verify the strict single crossing property, because the second derivative of U with respect to state and investment, as you can imagine, is negative, and that's precisely what we want to have. And here I'm citing Chow and Werning 2018 paper, who showed that existence of a stationary Markov perfect equilibrium in the quasi-hyperbolic discounting model for linear technology, I think, and small interest rate for general class of references, but for linear technology and small interest rate. So I think that this one is perhaps the most general that I'm aware of in the literature. But we could do more. So, for example, if you think that this beta impatient parameters is, for example, investment dependent, like in models with magnitude effects. So, for example, that you think that you are more patient, the more you invest. That's also a special case of these results that you've seen in the previous slide. But I've also promised that we can do non-additive aggregators, and that's true. For example, there in stochastic finance, people use so-called risk-sensitive preferences, where you have a non-linear aggregation between the current utility and the future utility, and this is done with the parameter gamma here. So these are well known from this literature, and this is also the special case of our result. And I'm also citing here the work of Obara and Park, who is studying dynamic games with recursive payoffs. So we also, as you can see, we're also contributing to that literature, but obviously we focus on the, let's say, games where at every period you have a single player, right? Single self making a decision. But I think that the Obara Park is the only reference I found for models with recursive payoffs in games. All right, so I think I have a few minutes to sketch you the idea of a proof. Obviously at the broad level. Well, the point number one is the one I owe you to tell, that we, when dealing with the unbounded utility functions, we are applying the ideas of local contractions due to Rico Zapatero, Rodriguez Palmero, and actually the correction by Novak and Matkowski. So that's one. Now, well, we take a standard approach. So basically, we take the C star to be a projected policy for the future generation. So we evaluate U star, and that's that's easy because here we apply the Bellman equation, the standard Bellman equation, so that we have U star, and then we argmax the V aggregator as and down with the C tilde here and the C tilde here. As then you can see, well, we are not taking the whole correspondence, but we take a particular selection. And in particular, for these models for these assumptions I presented to you previously, we take the least consumption selection, and or the greatest investment selection, if you want. And I would go back to that point in a moment. And well, what is this, the function space we work with? Well, yeah, we work with, well, investment, we work with consumptions that are such that investment is non-decreasing and upper semi-continuous. So precisely the greatest selection of investment you can imagine easily, it's if this is monotone, the greatest investment selection would be upper semi-continuous. Now, we do it for technical reasons here, but also for some sort of a normative reason, I would say. Recall that, as I mentioned when I was discussing the difference between the stochastic or the game theoretical approach to time consistency and that of decision theory, I mentioned that, well, we have to be careful when we deal with indifferences. And how we distinguish them and how we resolve the indifferences. And that's precisely what we do in the paper. Please observe that by taking the least consumption selection, we are basically taking the greatest investment selection, which in models of present bias, so the beta less or equal than 1, it means that we resolve indifferences in favor of the earlier selves. So that's precisely as was proposed by Strotz or Kaplan-Liachi in their paper. So that's why we also link the stochastic games approach with the decision utility, because the selection and the particular selection we take has some, I would say, normative considerations. And well, perhaps at this point, I will go back, if you allow, to this formulation. So see what happens. Obviously, if you want to show existence and make sure that this, for example, maximization operation here is well defined, I mean, it's not empty. Well, you need to assure at least that the U star, it's upper semi-continuous. Now, how we approach that? Well, yeah, if beta is less than 1, this corrective factor is it's negative. And precisely, we want to have C star, so the continuation utilities, against which we best respond, to be lower semi-continuous. So that's why we precisely take this particular selection to make sure that the U star is actually upper semi-continuous, and we can prove existence in a deterministic model. But I should mention that whenever we, for example, think of a future bias, so where the beta would be greater than 1, then according to what I told you, you should resolve the indifference by taking the greatest consumption selection and the least investment selection, and then we would take in our proof actually the greatest selection, right? So you can see that there is some link between the technical arguments that we apply in this proof, but also the ideas that I mentioned about resolving indifferences in recursive approach to time consistency. All right, and then we obviously show that this set is convex and most importantly weakly compact when endowed with the by this I mean when endowed with weak star topology. And just to remind you, this is the topology we use. This is the topology in which convergence is characterized by the convergence at every continuity point of the limiting function. And that would be important. Why? Because as you could see, we are working in models where we have monotone investments. So the investment policy will be in monotone. And that means that the number of such discontinuity points will be countable. And that's also the idea or the underlying the role of the underlying role of the assumption. I told you that we want to have the number of investments leading you to a particular state being countable, and then we apply the Schauer-Tikhonov fixed point to prove existence. And it's not mistaken here, it's not a typo. You see that C star is equal to BC of C star because remember, BC is not the correspondence, it's a particular selection we designed for the problem we want to solve. All right, so that's a sketch. Right, so then, well, I mean, I promise you that we can be more general. So one idea to be more general is that to allow for a little bit more time inconsistencies in a sense on non-stationarity of your discount factors. So here is the model of beta 1, beta 2 delta, which means that between the first and the second period you apply beta 1, beta 2 delta, right? That's your effective discount factor. And then the next period, it's only beta 2 delta. And then you are stationarily and consistently using delta only. So now you have three values, right? You have the U, which is the recursive part, which I call the recursive utility here, U star. You have V, where you have beta 2 delta. And you have W, which is the current self-preferences, beta 1, beta 2 delta V. And then if you think, well, can we again write the similar functional equation that is somehow linking the strategic and the recursive aspects? And the answer is yes. Obviously now the corrective factors are more complicated, but not too much. Well, you need to apply them 2 times, once to the current utility to adapt for changing preferences between today and tomorrow, and then for the next period utility to account for changing preferences between the next period and the next period. So then, and then you again have a single functional equation where you can use to verify existence. Now here the problem is a little bit more subtle because of that continuity, upper semi-continuity of the objective. Please observe that I have to be a little bit more specific because, well, I have this similar corrective factor as I had before, so minus U of C star, but also have next period one, which is evaluated at the current investment. So to apply the same technique, I would have to assure that both C star and the investment, it's actually lower semi-continuous. But that means that they are actually continuous, and that is a problem. That is generally a problem. So what we do is that we specify the transition a little bit. So for the special case I mentioned, so that we want to make sure that Q is non-atomic. We want to make sure that Q is non-atomic, and then we are done. We can prove existence of stationary Markov perfect equilibrium. What is the role of this non-atomic noise? Well, as you can imagine, we are basically assuming that the number of discontinuity points has a measure 0, and yeah, that's one of the roles. I mean, in the proof. So here we actually cannot prove deterministic we cannot prove existence for deterministic transition. We somehow need to adapt non-atomic transition to that problem. But you see the role why. I mean, do you see the reason why? So we can produce counter examples, right, to existence without that assumption, obviously. All right. Once we did that, we can obviously do even more. We can do what is sometimes called the semi-hyperbolic discounting, which is like the hyperbolic or the quasi-hyperbolic, but just applied t times, meaning that you think that t period ahead from now, you would have this delta discount factor that is stationary. But before that, you are following this beta delta kind of transitions, right? Beta 1, beta 2, beta 3, and so on. And again, it happens that this is the special case of what we do. Well, obviously, you have the recursive part, t periods ahead. And then you construct the argmax where you are argmaxing against u star, but just composed appropriately to account for these changing preferences. And this is done here in the slides by this operator AT. So you have to adapt a t minus 1 times until you get to u star. And again, we can write the functional equation. I didn't put it in the slide, obviously, but the idea is presented here, I think, quite nicely. So that and we can prove existence in this model of the same solution concept as well. And this is done here. Again, I need to have no atomic transition. So basically, I need a no atomic transition whenever this misalignment of preferences is more than 1 period ahead. So the beta delta is, you see, a special case where I don't need that. But if you allow for inconsistency to be more than just 1 period ahead, then in any of those, I need no atomic transition. Otherwise, the assumptions are somehow standard, and the strict concavity of utility function is basically the driver for strict single crossing properties between the investment and consumption, and we are done. So actually, as the theorem says, we prove existence for any t greater than 1. So the t equals to 1 is the exponential discounting, t equal to 2 is the quasi-hyperbolic discounting, and then right. And obviously you may wonder what happens with the t is equal to infinity. So we do the limiting case as well. So we do the limiting case by basically computing those betas and obtaining what we call the effective discount factors, delta 1 upper left script t. That is the effective discount factor, and then we can take the limit whenever it makes sense. So these products are defined. We can actually take this consistency period, I would say, or this the recursive part to be satisfied at equal to infinity, so that basically we'll have inconsistencies in every period. And then we can obtain the effective discount factor, the deltas, right, which was the one that I started with from the very first slide, when I talked about this behavioral discounting. So this approach is nice because it's not only it proves existence, and it's in this theorem here, that we can prove existence of the stationary Markov perfect equilibrium in any model for any t, actually, right? So for any t, including t infinity. And moreover, that's interesting, moreover, that any limiting point of that sequence of equilibria, or if you want to pass to subsequence, if it's not convergent, any limit point is also the equilibrium of the limiting model. So it basically shows some sort of an upper semi-continuity of the equilibrium graph of the equilibrium correspondence with respect to t. Remember, t is not the horizon. T is the moment at which you think you will be, let's say, stationary or patient, right? And adapt the exponential discounting. Right. Well, yeah. Here we also need assumption, obviously, but I didn't mention this. I didn't concentrate on this too much because, well, the assumption is somehow inevitable in a sense that you need to make sure that the series is well defined. That means that, f is if we allow for unbounded returns and general discounting, it could be that that the sequence is not well defined. It's basically infinity. So we need to make sure that we bound basically the discount factors. And eta, I think, was not defined on slides. Eta is that eta t is the greatest reward you can get within the period. So that's a bound of the period preferences in period t. So whenever we bound it and we make sure that these sums converge or are finite, then we are done. So this is it. And yes, we can also do what I think is interesting. We can also do what I call the reverse engineering. So if you give me the sequence of discount factors delta, which are this behavioral, any behavioral discount factors, I can compute back the betas from the semi-hyperbolic discounting model, using which I can approximate the resulting equilibrium in particular, but also the model, but also equilibrium in this semi-hyperbolic model. That's very easy. Basically, you reverse the betas with the deltas, and you obtain this condition here. Well, in particular, you see now this is the condition that the ratio using which we define the misaligned preferences. Now there is one comment here. If you want to compute beta 1, you have to be a little bit more careful because, well, you don't have delta 0. And that happens that to compute beta 1 and to finish this computation, you need to assure that the ratios of deltas is such that in the limit they converge to 1. Yes, that's in a sense natural, because the semi-hyperbolic discounting model in the limit has the flavor of hyperbolic, right? Where of the hyperbolic discounting. So that's why that's perhaps the restrictive condition in this approximation when you do it the reverse way. And yeah, and this is another example that we have. So if you have fully hyperbolic model with no stationary structure at all, where the discount factors, effective discount factors are, let's say, 1 over 1 plus t to the power of beta. The beta here is obviously to assure that the series I defined is convergent. So think, for example, that beta is greater than 1 here. And then you can reverse it and compute betas. Well, you simply divide one over the other, and you very easily obtain the betas from the semi-hyperbolic model that approximate the hyperbolic model. And yeah, I mean, that's perhaps striking that we prove existence of a stationary solution to the hyperbolic discounting model. Okay, which so fully non-stationary model. All right, and one last result I have for today. Oh yeah, I think I'm fine with time. One last result, perhaps, or the series of results we have. I was perhaps too specific for this time separable aggregators. Well, actually, we could do more. These topological properties that we verify rely on, as I said, more general properties of the aggregator, and it could be itself non-stationary. So the aggregator could depend on T as well, which is one thing. And then the aggregator could have the second element, which is the corrective factor, as I called it. And then you can recursively aggregate these preferences and calculate the argmax and find the C star that is best response to itself and the U2, and the U2 is computed using U3 and so on and so on. So this is the most general existence result that we have in the paper. Obviously, we need assumptions which are similar to the one I explained to you. Obviously, we'll need the non-atomic transition because these inconsistencies they presented here are very, very general. But what is specific in this one is that we actually don't need to specify how this aggregator depends on the middle parameters, y, those corrective factors, unless they are continuous. So if you apply this continuously, those corrective factors, then you are fine. But then you need non-atomic transition, and then you have, and then you can prove existence. Obviously, we still assume the strict single crossing properties, so that we have every investment selection being monotone. Right. So this is it. And yeah, I mean, and here we can have many other examples if you want. So for example, there is a paper by Young who considers a sequence of discount factors of the following form: beta 1 delta, beta 2 delta, beta 3 delta. So it's like quasi-hyperbolic, but basically, you know, applied between every period. So these preferences are never stationary in his setting, and yes, and actually they are not the one that I expressed and I called semi-hyperbolic, because this R, remember, R was the limiting of the ratio of discount factor, and here it's never equal to 1 at the limit, so it is more general than that. So to overcome this problem with the R limiting to 1, we can actually apply the last theorem I showed you in the previous slide. Then we don't need to have this condition. So we can prove existence in such model. We can also prove existence of, again, Markov and stationary in models with backward discounting. So here there's our preference, some sort of a reduced form preferences in the model of Ray and co-authors, where T is the period in your life that you suppose type and you somehow reassess your utility streams looking backwards. So so let me start with the easy thing. So for example, here from the large T on, you are stationary and you are applying the delta discount factor, and you are fine. And you know, I mean, that looks strange, but if you multiply this by delta T, you get rid of this, and this is standard exponential discountant from the period, let's say retirement age, T plus 1 on. However, before period T, you are having these preferences, where you first evaluate every utility using standard discounting, let's say, with the weight alpha, and with some other weight, let's say 1 minus alpha, you are looking backwards from period T back, large T backwards, and then you see that either your discount factor or your preferences are, you know, changing in a non-stationary way, at least up to period T, and you have to take care of this. So as you can very easily imagine, that's also a special case of our model with this VT aggregators that vary with T. And yeah, that's also applicable here. The next one I can mention is that, well, I mentioned already about magnitude effects, but we can be more general than that. Then the beta is investment dependent. Any of the deltas could be, for example, investment dependent. Well, whenever they are continuous and increasing, we can also apply to such behavioral features that you think that, you know, the more you have in the future or more you invest in the future. Well, yeah, the delta could be also state dependent if you want, and then we can apply our technique as well. And final, well, yeah, the special case of this model is perhaps the most obvious one is if you think about the class of bequest games, where you look T period forward for your next generations, and then for the others you apply the discount factors equal to 0. That's also fine. That's also the special case of what we have in the paper. So as you see, I mean, we have a variety of applications of this technique to prove existence. In the paper, we don't call it subgame perfect Nash equilibrium. We call it time consistent equilibrium, somehow linking the equilibrium approach and the time consistency from the Strauss paper, because of this, the way we break in differences. All right, so let me somehow conclude this slide. Yes, we proposed the new functional equation method for proving existence in the very general class of models, including this behavioral discounting features. The models could have recursive payoffs. There could be unbounded above in terms of rewards, and yeah, I think I stressed already how we link the dynamic and stochastic games with decision and recursive utility. And the two notable examples that we are proud of is the deterministic beta delta quasi-hyperbolic, and the stochastic, I should write stochastic hyperbolic discounting problem. Right, so I would stop here. Perhaps you have some questions or comment. I would be pleased to hear them or to answer them.
Thank you, Lukasz. Questions?
I have one question. So for your existence results, you had these 5 conditions, and the fifth one was that the number of i's for which the x has a positive measure, right? That it's countable. So you came back to this in the proof where it was used. I'm just curious, but not only for these conditions, but maybe for the other conditions, how easy to construct counterexamples when one of these conditions somehow not true to the existence result. So suppose that this is not correct, for example. Is it very easy to come up with the counterexample? How much is it needed for the proof itself? And how much is it? So how much room is there for further extensions? Maybe it's a very easy question. I don't know. So,
no, thanks for this. Actually, what we can do I would say easily, is to produce examples where in this space that we work with, your argmaxes are empty.
Right.
So we cannot adapt, let's say, the general, tools like the fixed point theory to prove existence. But that doesn't mean that there are not, that the argmax is empty for some, selection that we construct. To be useful for our proof or counterexample, that doesn't mean itself that there is no equilibrium, right? And so I would answer this way: we can very easily construct examples whenever of those is not satisfied to non-existence. I mean, not to non-existent, to the empty valuedness of the argmax, right? And then to prove non-existence, that's hard, right? That's very hard, actually, I would say. So yeah, that's not easy. Yeah, so that's, for example, this one. For the strict single crossing, again, well, I think this is the most general, very general class of preferences that we can work with, in a sense that the investments are monotone. For example, consumption in our models are not necessarily monotone, and it's also documented that in many models, the consumption is actually not monotone because of changing preferences. But you invest more when you have more. So this is the assumption that is giving us that. However, if you don't like this assumption and you violate that, then again you could have very easily construct problems, because this condition is precisely, as I said, guaranteeing that every investment selection is monotone, and it means that the number of discontinuity points is countable. Right. So together with this assumption, that means that the number of actually investments today oh yeah, I should mention, we also have to be careful whether these discontinuity points are not somehow not propagating over time. So that's the condition that is doing the job here. So yeah, I mean, again, if you don't like, for example, this assumption, then yes.
I do. I'm not against the assumptions, just to make
well,
sure
I mean,
that
if you have, I mean that if you have examples that are not fitting that framework, right? That's what I mean, right? But I should also be honest when it comes to limitations, for example, of this approach. I don't know if this was visible here, but if I stressed it enough, that what I'm just saying and how I characterize the properties of investment, it's true, well, generally in this paper, for the class of investment savings investment models where the state space is single dimensional. In fact, every investment policy in our model could be associated with the distribution. That's why we can adopt the weak, or sometimes called the weak star topology, identify this with a set of distribution functions. Now, if you think about multidimensional, like two-sector economies, for example, or multi-sector economies, that's a little bit harder. We are working on this, but obviously that would be not the same part of the same paper because it's very, very different. But that's also limiting, right? That's also limiting that we have a single sector economies here, and it's crucial to characterize and prove it. So, yeah, I mean, if I violate any of those, I can produce some partial counterexamples, let's say.
Thank you for this very informative and detailed answer. Thank you.
Yeah.
Lukasz, you have the nice existence results, and you have, even in your talks, you give many intuitions about the application of these results in economics. You mentioned investment, these many things. Do you have any idea that how these equilibria look like? So do you have at least an intuition that how to your results, I mean, the object of your existence results look like?
Yeah, so let me just answer at two levels in a way. One is that we prove existence in, where was that? In this class. So we have partial characterization of investment. That's, for example, not available generally if you adopt the self-generation techniques, or just focus on just sequential equilibria. So that's one thing. Secondly, remember that all our solutions are Markov, so they have very short memory, and potentially from the numerical or computational approach, that's very strong property. However, our approach is purely topological, so it's not obvious how to compute those solutions, right? So it's not that easy. I mentioned that we are somehow working on the related characterization using the self-generation techniques. And then we have some idea or how to perhaps compute it. But remember, what we do here is it's not explicit here, but you can imagine. I think that what we do is, in some sense, we work in the equivalence classes, in a sense that whenever the investments are not continuous at the particular point, there could be many things that can happen, right? We have a particular way of selecting this, and what I like about our approach is that we actually do it in the constructive sense, a little one constructive sense, in the sense that we take the greatest, for example, or the least selection, right, if indifferent. So it also gives some hints for the computational computational techniques, right? But obviously, so that's, you know, how would I defend our results in the view of your question. But obviously, if you want to have a very precise answer, like, you know, how this policies depends on the beta or delta in particular period, and whether I can do comparative statics or something, you know, we don't have it, right? We don't have it at the moment, and that's hard, right? Because precisely because of the number of equilibria that are potentially, you know, in this, that are possible in this one, right? I'm somehow interested in this and somehow optimistic about this approximation result that I presented, that we can define the sequence of somehow simpler games where your time inconsistency is somehow limited to only t periods ahead to approximate more general models. Remember that result, right? So that is, again, has some potential for numerical characterization, but otherwise, yeah, I mean, obviously you're right. I mean, we don't know much about how these models behave generally, right?
Thank you. I don't have any problem that you don't have a precise characterization. Of course, I just perhaps you're an intuition or something, but thank you for your answer.
Well, yeah, I mean, this monotone investment, let me just finish with that. This monotone investment is crucial, for example, to characterize steady states or invariant distributions or stochastic steady states, if you like to call it, of the capital stock or the states or the production stocks in these models, right? So we can say something about this in view that the investments are monotone. Yeah.
Thank you.
Thank you, witness. Yeah.
Further questions or remarks? Then thank you again, Lukasz.
All right. Thank you for listening. And if you, I mean, the paper is available at the web page. So if you have later thoughts about that, please feel free to contact me. Thank you.